Hi, my name is Jordan Snyder, and today I'd like to talk to you about fitting a curve to data. We're going to cover this both from a theoretical perspective and as implemented in code with Python using the packages NumPy and Matplotlib to visualize the results. So, let's set the stage. First, we suppose that we have some data. Our data are going to be denoted xi, yi, where I runs from 1 up to some number n, where n is the total number of measurements. The idea here is that there's some relationship between x and y, and we want to discover that by looking at our data. So, we suppose a model. So we believe that there's some relationship between x and y, and we want to discover it. And to do that, we need to specify what kind of relationship we expect. And that's encoded in the model. So the model says that yi, the y value for each sample, is equal to some function of xi plus some measurement noise. Okay? So specifying the model amounts to specifying what class of functions we're going to consider. For now, we're going to suppose that f is a polynomial function of x. So our modeling assumption will be that yi is approximately equal to a polynomial of x, and I'm going to write it in terms of its coefficients, a0, the constant term, plus a1x plus a2 x squared, and these should all be xi's, all the way up to am x to the m, where m is going to be my maximum degree. The approximately equal symbol is a stand-in for the fact that this will never be exactly true for all data points because there is some noise and this function might not exactly capture the true relationship between x and y. So finding a function f that relates x and y in this case boils down to finding the coefficients of this polynomial function. So these are our unknowns. So a0 all the way up to am. Okay, so our task is to use the data to find coefficients of a polynomial that approximately describe the relationship between x and y. So how are we going to do this? Well, I said that these coefficients should have the property that this equality is approximately true for all sample points I. So we can set this up as a system of equations. What we can notice is that the right-hand side depends linearly on the unknown coefficients a. So we can use that information to actually set this up as a linear system of equations. What we have on the left-hand side are our data points yi, so we have y1, y2, all the way down to yn in a column vector. And this column vector is equal to a matrix times our unknown vector of coefficients. So that's a0, a1, all the way down to am. Now, what are the coefficients that we should place here? So let's consider setting I equal to 1 and looking at what we have. So the first entry of this first row should be just the number 1. The next entry, that's the thing that is multiplying a1, that should be xi. In this case, I equals 1, so it's x1. Then the powers of x keep increasing as we go along the first row up until we get x1 to the mth power. Likewise, for the second row, it's the same thing, except we replace the subscript 1 with the subscript 2. We still have a 1 in the first column, then x2 to the power 1, up to x2 to the power m, and so on down the rows. 1, xn, and then xn to the power m. this system of equations, if we place an approximately equal sign here, is exactly equivalent to this set of approximate equations denoted up here. So we can write this now as in vector form by saying y vector, that's all n entries of y, equals the matrix M that depends on the data x times our unknown vector A. So this is what we hope is true. Of course, it's not going to be actually true because we may have many more data points than we have possible coefficients to vary. So in general, this is an overdetermined system. So in this case, rather than solve for an A vector that satisfies this equation exactly, we'll find the A that minimizes the residual. So we will solve the following problem. We'll minimize over A vectors the quantity y minus m of x times A squared. So this is known as a least squares problem. And when it comes time to find this solution in code, we're going to use the fact that this is a well-known type of problem and call a function from the NumPy package that solves it for us. Okay, so with all of this background established, let's turn to the code. So this is a Jupyter Notebook. So you have code cells that will run, and then the output appears beneath the cell. So the first thing I'm going to do is import the packages that I need. In this case, that's NumPy as NP and Matplotlib as PLT. And I'm going to set a dark background theme for Matplotlib so that it shows up well on the lightboard. So I'll just import those packages. Now I need some data. I need my xi and yi. So to do that, I'm going to generate some random numbers as my x's, and then apply a function to get y's and add some noise. Because what we really hope is that the y's are a function of x plus noise, so I'm going to generate some data where that is really true so that we have something to find. So here I'm setting up my parameters. Here I have n equals 100, that's the number of data points. And then I want to specify the range over which I want my x values to lie. So I want them to be on the interval 0 to 2, just because I like that interval. So I'm setting x min and x max equal to 2. I'm also setting a noise level, so that's the amount of noise that I'm going to add. And now I generate random numbers. So in NumPy, the way that you do this is through the random submodule, so np.random, and then you create a RNG, or a random number generator object. In this case, it's the default RNG. And then once you have the RNG object, you can tell it to give you a random sample of length n. So by default, the random sample is a uniform distribution over 0 to 1. So I'm going to have to take those random numbers and multiply them by 2, essentially. So this line is what does that. So I'm multiplying by the width of the interval x min to x max, and I'm shifting it to the right by an amount x min. In this case, x min is 0, so I'm adding 0. So these numbers, the x data is a 100 length vector with uniformly random numbers from 0 to 2. Next, I'm going to generate my y's. And to do that, I'm going to create a vector called yTrue, which is some polynomial function of x. In this case, I picked x squared minus 2x plus 1. And then I generate noise to add to it, again with the RNG object. In this case, what I'm doing is taking a standard normal, so this is a Gaussian distribution with n samples, and I'm multiplying by the noise level of 0.2. Then finally, my y data are the true y values plus noise. So I've set this up so that my data are exactly of the form that I assume that they are when I've derived my regression problem. Okay, so let's run this cell. So now we have x data and y data. And what I want to do at this stage is just to quickly visualize the data. Okay, so x is on the x-axis and y is on the y-axis, and you can see that you can see some relationship between x and y, but there's quite a bit of noise. So at any given x value, the y values range quite a bit. And the magnitude of that range is on the order of 0.2, since that's the noise level that we picked. So our task in regression is to draw a polynomial function through this set of points that approximates it well. So let's go through our model fitting. Now, we have to make a choice when we think about polynomial regression. Specifically, that choice is what is the maximum degree we want to include in our model. In this case, I'm going to pick m equals 3. So I'm going to have up to third order polynomials, so up to cubics. And that means that if you look at how this matrix is constructed, I have the 0th power, the first, and so on up to the mth. So since I'm starting from 0, the number of columns is 1 greater than the maximum degree. So in this case, I'll have 4 columns in my matrix and n rows, so n equals 100. So now how do I build this matrix? I could do it in a couple of ways, and I've shown 2 here that I'll walk you through. So first I need to create a matrix of the proper shape. That shape is n, the number of samples, by m plus 1. So that's the number, sometimes we call that the number of features. Now, what I can do is loop through every individual element. So in the ith row and the jth column, the entry is the xi value raised to the j minus 1 power. So in the first column, j is equal to 1, j minus 1 is equal to 0. So I'm taking x to the 0, x to the 1 in the second column, and then x to the 3 in the fourth column. So I can just do that with a nested for loop here. So I'm looping over all the rows, looping over all the columns, and setting the ij element of the matrix to the jth power of the ith data point. One thing to note here is that Python is 0 indexed, so when you loop over range of a number, you start from 0 and go to 1 less than that number. So this loop range of m plus 1 is going from 0 up to m. So it's exactly giving me the proper powers to put into my columns. Okay, so that's all well and good, but we can do it in a little bit more of a clever way. This is something that comes up a lot. I would call this doing this operation in a vectorized way. So the thing that I'm doing for each column is very similar. I'm just taking the x value and raising it to the same power. So what I can do is actually just loop over the m columns, and for each column, take the entire data matrix and raise it to a power. So when you do this, Python knows to simply apply the power operation to each entry of the vector. So it'll exactly give us these columns that we need. So these 2 loops are exactly equivalent in terms of the matrix that they produce. This one will probably go a little bit faster because looping tends to be a slow operation in Python. So when you are able to vectorize, it's advisable to do so. So let's just go ahead and run this cell and then examine the shape of m just to make sure we have it right. We indeed have a 100 by 4 matrix. And now, all that's left to do is solve this least squares problem. As I mentioned before, NumPy, within its linalg linear algebra package, has a least squares routine, and all that's necessary to solve it is to call numpy.linealg.lstsq, so least squares, and you need to give it the matrix M and the Y data. So these are your known quantities, and you're trying to find the unknown A. So we give it our matrix M and our data vector our data vector Y, and it gives out 4 objects. So this is the solution, A hat, hat meaning the best fit value. And then it also gives 3 other outputs. It gives residuals, rank, and singular values. So residuals, that is the difference. That's the difference between Y and M times A. So it gives a quantification of exactly how far away the model prediction is from the data. Then the rank, that is the linear algebra rank of this matrix, and that tells us about how well posed this problem is, and then the singular values are the singular values of this matrix, which also give us valuable information about how the nature of this solution will depend on the data. So we're going to run that. It runs very quickly. And the first thing we can do then is examine A hat. So we can directly interpret this vector of coefficients in terms of the model that it's telling us. So now that we have coefficients, we essentially have a polynomial model that approximates the data. So how do we read this? The first entry of the vector is the constant term, then it's the linear term, then the quadratic, and the cubic. So this is telling us that y is approximately equal to 0.85 plus negative 1.5x plus 0.45 x squared plus 0.17 x cubed. So we know the true coefficients, we happen to because we generated the data, and those would be 1, negative 2, and 1. So in this case, we didn't do all that well. And in particular, we have this term that's not in the true model. But of course, in general, you don't know the true model. This is all a fitting problem. We just have our data, and we need to find f. So let's go and compare the model predictions to the data. So to do that, I'm going to compute the model predictions. So what are the model predictions? The model prediction is this right-hand side, which I hope is approximately equal to y. Now, because of this derivation, I know that I can compute those model predictions by just taking this data matrix and multiplying by the coefficients. In Python, the way that looks is you can do it a couple ways. There's a matrix multiplication function, np.matmul, where you give it the matrix and the vector, or you can actually use the ampersand. Is that the ampersand? The @ symbol. Yeah, so the @ symbol also does matrix multiplication. So when you have a matrix at a vector, this is NumPy syntax for do the matrix multiplication. So these are both equivalent, and I've just written both of them just so you can see two ways of doing it. So these are the predicted y values based on our polynomial model. So what I'm going to do now is scatter the data against the prediction. I'm also going to include the true relationship just so we can see exactly how well we did, and the data themselves. So let's look at that. So what we have here is the data in yellow. These are the same data points that we started with. And then in blue dots, we have the model predictions. So you can see we have a much smoother, it's a polynomial relationship between x and y on this curve. So in a way you can think about this as the data with noise subtracted. And then for comparison, you can see this line here running through. This is the true model. This is something we didn't know at all in doing this fitting procedure, but it turns out that that curve lies fairly close to this model prediction curve. So to recap, we started with some data. We supposed that it's described by a polynomial model, and then we showed how we can write that polynomial model as a system of linear equations. Then we solved that system of linear equations in the least squares sense because it's an overdetermined system, and we used that solution to generate predictions that we can then compare to the data, and in this case we can compare also to the true model. So thanks for watching, and I'll see you next time.